Hello and welcome back to ST118 Statistics and Applications, Session 9. In this session, I'd like to discuss with you the subject topic of the case when time uh, is involved in regression. Right? We all understand that time is money and time drives everybody's lives and all businesses. And so it turns out that it also drives a lot of the data measurements. And since we are always measuring data, capturing data, and put it into our use, right, in terms of finding out the coefficients through linear regression, then we should take a look at it. It turns out time does have some special influence on the way we deal with it mathematically. Not just that it is physically driving all the measurements and driving the growth and driving the withering of businesses and data, but it also needs to be treated with respect, all right, especially when we are putting time as a variable into our linear regression models. Okay, so next we want to talk about the models that include time. All right, applications. These might be examples and to see how they play a part. And well, we would then talk about the auto correlation as a property that is causing issues and therefore that we have to pay attention to when we put in time as one of our explanatory variables. Okay, and then of course we want to learn about Durbin-Watson test for autocorrelation of errors in the linear regression model. Okay, and of course we can always look at an example, a simple example. Okay, and of course all these calculations are all available in open libraries. That means you don't have to pay a fee or software purchase. In Python, in R, all of high quality computations, high quality in the sense that they are optimized, they are fast, they are also reliable. That is, the numbers that come out, you don't have to suspect that they might be having some bugs inside, and that don't take it for granted uh, that it's always bug free, right? Especially in the earlier days of the library development. So in my days when I was learning stuff, sometimes we get an answer that we ourselves suspect didn't look right. Turns out there was a bug, right? Because the programmer didn't quite understand the mathematics behind, or it wasn't tested fully, or it is complicated, right? The math is complicated. So while 80% of the calculations are done, there is always this 20% part that is always rather tough to get it right or something like that. So, but then, we do have very high quality functions and libraries available these days. And so to do any of these, they are straightforward. So this example, just like all simple numerical examples in my videos, they are meant for sort of a slow motion, frame by frame, right? Analysis to see how the numbers move from one place to another, so that we, at least for once, right, in our lives, get to see how the numbers are being computed and thereby developing a better inner feel, right, of how to interpret the results when they are very quickly calculated. And then we say, oh, okay, with this number, what do I do? And we then know what to do. Okay. So let's get started with the idea of when time is involved. Yeah. So in our example, we of linear regression, we've been talking about wanting to investigate, explain, or predict, right? So using the regression model. Once we collect the data, we pipe it into the functions to get the coefficients. Then we look at the test results, right? Model is good, variables are performing, and they are significant. Adjusted R square is good, and so then we rely on it to do our investigation. So we could use the model to identify which factor is driving that response variable. We could use the model to explain, right, the strength, right? Oh, this is the primary reason, right? We, of course, the model doesn't explain the reason. We are not doing the why here in our linear regression, but through our contextual interpretation, we can attach a reason and say this is of primary influence of our y variable. This is the secondary. This is the third, you know, factor that is driving our response variable. So when time is involved in regression, right, we will put in the time variable. So for example, perhaps we might want to say that health, right, the health of a person can be explained by some B0 plus B1 of the person's weight and income, thinking that, you know, we all know weight of a person affects the person's health a lot, right? If obesity is one such a problem, right? So if you're overweight, then it affects your health. We might also say that, well, if the person is unwell and you have high income, then you can afford to correct your weight and thereby, you know, recover your health or, you know, improve your health. So we look at this as a health index, the higher the better, weight, right, and then income. So we are trying to establish this relationship. And this might be okay, right? This might be okay because we might have a demographic, right, in the city, in the population that has varying income levels. We're not looking at the ultra rich. We're looking at, you know, perhaps the middle quartile, right? So there's a good variety of income levels. There's a good variety of weights, right? And we study this, so that's probably okay. However, there may be a particular segment of people, right, where the income and the weight might be correlated. So if you're looking at sumo wrestlers, so the heavier you are, it seems to be that you're paid more, right? Because you tend to be able to win whatever sumo fights they are doing. So they really add on to the weight, right? And if you have high income, you can add on to your weight and so on. So, but of course, does it make it less healthy for that sumo wrestler? Maybe they, since young, have been training their bodies to take it, so their health is not too much affected. I don't know, right? So what I'm trying to say is that if you are looking at a particular segment, then maybe we can't tell so much anymore. They might be related. Then in that case, we have multi-collinearity. We learned about that, right? So all that stuff, all the 5 assumptions of linear regression, still apply whenever we perform linear regression. So far, so good. But then here comes the new kid on the block, right? The moment we add another variable, but this time round it is time. Right now what happens? Because when time is added, we might think that, well, as time progresses, we just take the samples, and time is a variable just like any other, right? The important thing to realize is that time is not really just like any other variables. The first thing that is already very different, right, is that time variables, they are always ordered, or time 5 is always larger than time 4. Our time here doesn't have to be a calendar date. It is almost always uh, kind of coded into integer variables. So with fixed interval measurements into time 1, time 2, time 3. So time 5 is always after time 4 and before time 6. But when we do statistics, we do averages, we do sum of squares, right? We do all the errors, right? If you recall, that's why knowing the formulas and the mathematics behind is always a good thing, even though we may not have to recall the details, but you must have heard of our discussion about sum of squares and all these, right? So the thing is, sum of squares, summing, finding average, all these don't care about the order. But time data cares about the order. And when we put in time here, it's the order is being discarded or ignored when the order does matter. Correct or not? For example, to find the average income, we just average it up. But when time is involved, you want to it becomes not reasonable to average your future income with your uh, part-time income when you were a student, right? And then say your average income in your life is $4,000 per month. It's very maybe it's quite a meaningless number as far as anyone is concerned, right? The average income in your life. So because it doesn't help that particular individual to plan or do anything, right? And it's like just jumbling up all the future and the past together and then coming up with a number. So when time is involved, we need to be careful with a few things, right? We need to interpret it carefully. We need to uh, look at the meaning. Does it make sense or not, right? So typically, time will be added as two kinds of variable. So you can add time as a quantitative variable, right? So which is what I was saying. Time 1, time 2, time 3. That's called the time series way. I'm not talking about intervals, right? Time intervals is just an interval, so that's fine. Time interval is not an issue, but absolute time stamps, right? So that's going to cause the problem. Time intervals, the duration as we call it, is not so comparable. For example, you take uh, 10 minutes to run 2.4 kilometers, right? I take 15 minutes to run 2.4 kilometers. That's fine. You are better than me, right? You take lesser time than my time interval. So that's fine. You take lesser duration than my duration. That's comparable, right? So that's totally no problem. And then I train. Perhaps I can run, I don't know, 9 minutes 50 seconds, right? So it's in a way independent of age, independent of the race, independent of so long as but maybe highly dependent on training and training hours and the instructor or whoever, right? But whatever it is, I'm not talking about time duration. I'm talking about the time stamp. So for timestamp, we can put in the time series, right? We can put in the quantitative timestamps where you minus the two timestamps, we will get a time duration. But typically we put time series. So for time series, then it's always unit interval in between, and we have to exercise the discipline to always capture the data every minute, every hour, every day. So daily sales, for example, is a time stamped quantity, daily sales. So every day we have a time. Every day we capture the total sales for that day. Stock prices, So goes by tick, 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 right? So if you are at the trading floor, you have a trading terminal, it gets updated every second, then the timestamp is having a unit interval of seconds. So that would be quantitatively. You can also add in time variables as a qualitative label. So you can treat it that way. So such as the time when it is 1, time when it is 2, and all these are 0, 1 variable. So you turn on, turn off that time. And because you're capturing multiple occurrences of people of certain weight and height and health, right? At time 1, time 2, time 3, time 4. So if you want to add, and suppose the time is measured by years, then it makes sense to say that, okay, let's analyze the second year after the participants enter into our program. So what happens? What about the third year? So we switch off time 2 and turn on time 3 and so on. It means you are treating each time stamp as a population. So as a population of health, weight, income, and that's it. No, so in some sense, the time disappears. We're just looking at the time 3 population, the time 2 population. So after we turn on that time 2 and turn off all other timestamps, then we're only left with time 2. That means the second year, the participants are involved in our program of study. What was their health, weight, and income numbers? Then we do regression. Right? So then it basically means if we have 10 timestamps, that means we study the same group of participants for 10 years, then we have 10 regression models, one for each year in that sense. So essentially, that wouldn't cause a problem because the time would have sort of disappeared, right, into our proper handling of the time series. So that part is not a problem or less of a problem. So that's not what we are going to focus on. Not so much a problem. Problem in regression, I'm just saying. Okay, but this would be where all the issues come in. So what are the issues? Well, the issues could be that we have what we call confounding, right? Confounding. When you add in time, right, then suddenly you think about it, or maybe after doing a sort of a naive run of the regression model, the numbers come out and you think about the numbers, the coefficients, you find it very odd, very strange, huh? Or the p-values suddenly make the whole model very bad, not significant, right, or something like that. And then you think about it, it's because probably time is also driving the income and weight. So time is driving income and weight and then driving health. For example, when you are younger, you tend to, that means all else being equal, right? That means you don't pay attention to your weight, we don't care about the income. Our biological body tends to be weaker. We catch a cold more easily. We suffer from fever more frequently and more lengthily. We recover slower than when you are a strong young adult, right? So your immunity rises. This is all biological. It's not about weight and income. Okay, you could be obese, you could be having high weight, low weight, but your immunity compared to your younger self is always going to be higher. Yeah, simply because you are having more body mass than your younger self. Even if you're skinny, right? Your skinny young adult body size is still going to be stronger, right? Heavier than your skinny young teenage or child age body. So the immunity and all that stuff, as time passes, your immunity and all that, so your health on average increases already. Your income, and if you capture the correct segment, or rather the wrong segment, then that is the time when your income grows, right? Very much with the passage of time, right? Like example, if you are age 16, 17, you're somewhere in the high school, you're doing well in class, so you want to earn some part-time uh, income. That's fine, right? And you cannot almost by the arrangement and the fact that you're a full-time student, you cannot be working full-time. Legally, you probably cannot be hired as well. So somehow by human rules, right, you cannot be earning a high income. So you can earn part-time income, which to you might be a lot. But if you look back now, assuming you are now 20 plus, right? So you look back, that's not an income, right? But at that time, 14, 15, 16, 17, you earn some money. That's like, wow, right? A big welcome side income. So as time passes, you pass 20, 21, 22, right? And in university, even if you do side income, part-time tuition and whatnot, walking the dogs, mowing the lawns and all that, you can earn more, right? Because people know you are of higher age, you are more intelligent, you are more adult, right? You understand contextual reactions, even not taught and not told. For example, if you walk the dog, at the end of walking the dog, the owners will not teach you or brief you, but you somehow know that you should, you know, bring back the dog, tie it up properly, maybe give it a bowl of food and water, and then you lock up the place so that the dog will not be starved or whatnot before the owner comes back later on or something. If you're giving tuition, right, and the parents might both be working, and so nobody is at home, uh, you know, the customer, that is the student, the young kid, would then open the door, and of course the parents will expect you to also look after the house in some sense, because while you're giving tuition, some stranger wants to come into the house, they should have that peace of mind that, oh, you are adult enough to know that, hey, even though this is not your own house, you shouldn't let strangers in, something like that, right? So these are like common sense thing that, okay, they would then pay you more than they pay a 12-year-old kid to help to give tuition. A 13-year-old kid, a genius, right? But to help to give tuition, but not enough life experience, right? And you have the life experience. So you're worth more. So whatever the thing is, I'm trying to say, as time passes, your income increases. Yeah? Your health improves. Even if your income didn't increase, even if your weight didn't change. Right? As time passes, your weight increases. Because a few things. You choose the wrong timestamp. You choose the wrong study profile, the population profile. Right? Wrong timestamp because the time you choose, right, is 1 year by 1 year basis. So over 10 years. So it's a long experiment with good funding, fine. But it's a long experiment when the variable that you also includes, the weight here, changes or shows significant changes. Right. So over a decade, for a teenage, he or she will grow right into a young adult, and that time period, the weight could increase. Right. Maybe not as drastically. Not the gradient is not as drastic as when a baby grows to a young child, but teenage to grow into a young adult, there can still be weight increase. Whether you are increased because you have more fat, become obese, because you eat more, you can afford more snacks and more unhealthy food to eat, or you can afford to go to gym and have sports and you grow muscles, so you become heavier. Right? In a good way, you become heavy because of muscles. That's fine. But whatever it is the case, as time increases, weight increases. Or as time increases, you don't pay attention to your weight, right? Your weight decreases. But then because it's a long time study, your weight drops. But then it is still that means your 24-year-old body, right, extremely skinny, is still going to be heavier than your 14-year-old body. because you are the skinny DNA type, right? No matter how much you eat, you are still looking skinny, right? Fine, that's good. You might think it's good, but no matter what I'm saying, your weight at 24 years old will still be heavier than your 14-year-old weight. Right? So that's why it is called confounding. And that means we know contextually, the way I narrated to you, you would agree. I don't have to show you data to prove, right? So if I choose long enough time, then and I contextually the variables that I've included in the regression, they also experience changes, growth with time. Then we have confounding effects. Confounding effects simply lead to the breaking of the independence, correct or not? Yeah. So weight no longer become independent of time. That income doesn't become independent of time. As you grow, right? Your 14-year-old self cannot earn income. 60-year-old you earn a little bit part time. 18-year-old, 20-year-old you earn more part time. 22 years old you graduate and find a job, you earn more. 24-year-old you get promoted, you earn even more. So over this decade, you experience as time increases an increase in your income. Problem, right? So multi-collinearity comes in. So confounding is what we talk about, the contextual influencing. As time increases, weight increases, income increases, and for that matter, even health increases, right? But the mathematical level, confounding leads to multi-collinearity. Right? We talked about multi-collinearity in the previous video. Multi-collinearity leads to what? Leads to you still will get your B0, B1, B2. So you still get a model. But this model starts to get fuzzy. Or you don't know whether this is B1, B2, they can be trusted or not. Are they underestimating the health? Are they overestimating? Right? So that's problem. And when that comes in, then we cannot use this model very much, right? Hopefully, adjusted R-squared shows a bad low number. At least we get a signal. Now, worse is that adjusted R-squared also shows reasonable number, then we have a big issue. Because multi-collinearity wouldn't be readily or consistently discovered by adjusted R-squared. So because adjusted R-squared was calculated based on assuming there's no multi-collinearity, right? So that's why when we break those assumptions, all the indicators that we talk about, they don't, blink and show red light, warning, warning. You have trespass upon the assumptions. It's no longer reliable. No such thing, because it's a silent kind of cancer in the model itself. So the model doesn't know that your data had already broken the assumption. So that's the thing. And when we put in time, then we also put in something that don't quite occur if we don't put in time, which is auto correlation of the data of the Y's. As the response variable. So the thing is that many variables tend to change with respect to time in a way that is gradual and consistent. They don't sort of have wild changes in a short time. Okay. Of course, given long enough time, that's why the time period, the range of the time period and the intervals, how frequently are we sampling, make a lot of difference whether we suffer from the ill effects or not. Okay. In the previous case here, we were saying the confounding, right? If you are sampling quick enough within a short time interval, like university year one students only. Okay, university year one students, the income are all thereabout, right? So and we are talking about year 1 year time period. So there's not much of a time. So maybe we measure over 12 months, right? And so your income wouldn't be expected to vary by a lot, right? And so it will be more like, oh, I do tuition for 3 months, then quit already because the parents didn't want me to continue. I do another tuition for 6 months because the child graduated. That's why, and then I move on to the second year, right? So when the time range is short enough and the intervals are properly chosen, because we choose 12 months, not daily. Daily, right? Daily. Every day we go and measure the health rate. Then it'll be a lot of noise, right? Because day to day it would not change at all, more or less, right? We would all agree to that. We don't have to really prove it, right? So day to day your weight probably won't change by too much. So it's probably random fluctuation. Because if you if you weigh yourself before you go to toilet, clear your bowels and urine and everything, and then you weigh after that, and it's going to be like maybe 300-400 grams difference, right? So all these will be random in nature. So yeah, so that's not going to be very uh, helpful to your experimental goal. But then you wouldn't have confounding autocorrelation. So the thing is that if we measure the time, the range is long enough, and these variables, they do change rather drastically given the range, right? And then you sample, and the samples, right? If it's too frequent, then from day to day your weight won't change, right? Your weight won't change too much or at all. From month to month, it will change. It may change, right? Depending on whether you are increasing your weight, maybe consciously or subconsciously, or reducing your weight, right? So the thing is, when you have autocorrelation, first of all, what is autocorrelation? Autocorrelation means the health is dependent on the previous measurement of health. So what's your health this month? Okay. So in other words, your health this month, strongly depends on health last month. Can I say that? Of course, it may be also dependent on the kind of participant profile you pick, right? What is your population? Yeah. For baby health, right? So newborns who just grow without consciously taking care of their own health. That means they won't actively take precaution to maintain health, to sustain health, to improve health, right? Then very much it is kind of based on their own biological strength, their bodily strength, right, and also due to randomness. So a baby's health, right, next month is of course highly dependent on the previous month's health. A healthy baby next month can become slightly less healthy, right? A little bit healthier, but then there is so much so-called health you can go. You can't be going towards health, infinity health, right? Health as a measurement, say 100% is the best health. Let's say we all normal people, we are at 50. So the best you can go is 100. So there's still a lot of room. So assuming the maximum is not a problem, that means hitting a maximum is not a problem. So the baby next month could be 51 compared to this month 50. But another baby, right? Another baby that is less healthy. So this month is 40. Next month, better. Better would it be 50? Within 1 month, right? That's why the time drives a lot of the rate of growth, rate of improvement, rate of deterioration. That we all know, right? That we all know. So that's what, except we don't know what's the rate. So that's why we study this. But what the autocorrelation is that for health, for example, and for many measurements that are natural, not like health, like uh, weight and height and all these, and for that matter, society kind of measurements. That means it is human. It is in a way the participants are all human, so artificial. You can purposely don't go for income. You can purposely don't take care of your health, but collectively, it won't be the case that the whole population of Singapore, the whole population of a city, won't want to take care of their health, right? It won't happen that way. So that's why at a social level, society level, uh, the measurements of this society, this population, tends to be also depends on your previous value. Okay, so the health of this person is highly dependent on last month's health. Right, so that's what we call the order one autocorrelation. You depend on one cycle before. One cycle before. Yeah. If turns out that the health of this person depends because it's no longer just baby, but adult. So adults sometimes drink, right? Sometimes smoke, sometimes eat nutrient supplements to improve their health. Sometimes perform diagnosis very frequently, some of the health nuts, right? Then you will find that maybe the dependency is not just order one. So the health of this person depends on last month's health and last month health. Right? So then it will be order two autocorrelation. So is there autocorrelation? That is the question to be studied. That means we need a detector. The detector is certainly the Durbin-Watson test, right? But that's not to test solely for health. Durbin-Watson test is to test for this entire model whether the remnants, that is the residue, right, contain autocorrelation with each other. When the residues contain autocorrelation, then this current model is not good enough. Even if adjusted R square shows somewhat respectable number, it's not good enough because there's a big chunk of residues that are not being explained. That means your so-called predicted Y is very bad from the observed truth, the observed data. So we'll come to that in a while, but just trying to see what is autocorrelation, right? But first thing first is not only health that has this autocorrelating of order one, but also let's look at GDP, right? Versus time. As time passes, GDP increases. Fair enough, yeah. As time passes, GDP increases or GDP decreases. Hopefully not, right? As time passes, GDP increases. Now, as it increases, can it double? Is it possible that Singapore's GDP goes from 2025 some X number, 400 billion, 500 billion, to double it in 2026? Is it possible? Nothing is impossible, yeah, but does it make sense, right? Is it even in our discussion? Can government say we want to plan to double our GDP in 1 year's time? You can say that for over a decade, right? Oh, we want to do that, so we should focus on AI development, for example. You can do that over 10 years' time, but not over 1 year's time. We all would tend to agree to that. Why not? Why not over 1 year's time? It's simply because time drives everything, correct or not? Yeah. So we all know that time will not drive the GDP to such a drastic rise, or for that matter, drastic fall. Will Singapore's GDP become zero next year? Not impossible, right? But that would mean some sort of an externality like COVID-19, right? So was it 2020? There was a big dive in the GDP. 2021, big dive in the GDP, right? But also not going to zero also, right? But let's say it's so low that we can basically consider it zero. Fine. That's possible, but that's externality, which is a different case. So putting those rare but impactful externality events aside, those things that would disrupt the smooth progression of the linear regression model, then GDP basically grows in a way that depends on its previous value. If you think of GDP as a person's weight, if you have a high GDP at the start of the year, then you tend to also, right, because you have achieved that high GDP, you tend to also already have a population and the equipment and the land and the whatever assets to earn not only that, but more, right? More than your that year's GDP. So if assuming, suppose that year is $500 billion, and because you have gotten that $500 billion already in 2024, so it shows you your country already has the people, the talent, the equipment, the land, or the knowledge to use the land, the various stuff to be able to earn that much. Then you tend to be able to earn maybe 10% more. That's very high. 2% more. 2% of 500 billion, right? That's 1% would be 5 billion. So 2%, 10 billion. 10 billion more, which is very reasonable, right? It will be most, within what most economists' opinion to say, well, very plausible, right? And so on and so forth. But if your starting base is only 50 billion, right? Then we say next year we're going to have a increase in GDP. We'll do this, right? We already have the asset, talent, people, equipment, land to earn 50 billion. So we project that we will earn how much? So if you say we will project to earn 2%, people will be quite agreeable, right? Maybe that's a plan only, but then you say, okay, I earn 2%. So good. If you want to say you earn 10%, I want to earn 5 billion more. So we become 55 billion. 10%, right? 10%. People will start to raise alarm. 10%, are you kidding, right? So because that's going to like make your people work 24 hours a day, work 24 without sleep, right? Or have a lot more overtime, or you will need 50% more production equipment, which you can't afford to buy because you only have 50 billion of GDP to begin with, and so on and so forth, right? So it becomes rather unbelievable to say you want to grow by 10%. To say you want to grow by 5 billion, right? If you have a base of 500 billion for this year, plausible. Why plausible? Because it's 2% of 500 billion. From 50 billion, you say you want to earn another 5 billion. It's also 5 billion. But then we say not plausible. Not so. Why do we say not so? Because that is 10% of 50 billion, right? So we don't agree. But if we say 2%, then we agree. So you see, the way we describe GDP is we have a growth of 2%. We have a growth of 1%. Oh, unfortunately, there's a shrink of GDP of 0.5%. That kind of meaning. So we always use percent of the previous year, even in our discussion, even in news, even in reports, plans, whatever, right? We don't talk about the absolute. We do talk about, but you understand what I'm saying, is that the absolute amount matters less when you plan, when you analyze, when you explore the feasibility and so on, than the absolute value, than the percentage value. So that's why the percentage is based on previous GDP, and the way we say it that way already hints at us that the GDP is strongly related to time, and because we use percentage, that is another hint. It's not to prove that it is having autocorrelation, but it is a hint that you may have, right, a very strong autocorrelation. Okay, for that matter, we can also look at inflation rate with time. artificially created indices like inflation rate tends to defy gravity, defy physics. So, for example, stock prices changes with time, and if it's short enough time, for example, stock prices of a startup, a bank, blue chip company, which is very stable and all that, right? But short enough time, within a month, the daily changes, for example, right? Because within a month, we all know that the company's policy, culture, CEO, management, bonus scheme, whatever treatment of employees, customer base, whatever, right? Could hardly have changed much. Fine, day to day, there's always some dynamics, right? But over a month, you won't expect drastic change at all, right? Not yeah, but over 10 years, yes. Over 1 year, there will be some. Over 5 years, there'll be more. Over 10 years, a small bank can become a large bank, right? A multinational can collapse into a small bank, right? So big things can happen given enough time. So that stock prices, when you have short enough intervals, right? Like let's say daily stock price of DBS Bank over 1 month, whichever month you pick, right, over 1 month, consecutive daily prices, it will more or less be just random fluctuations, and it can not just in a very rare instance, but uh, sometimes money flow in, right? You don't know when, but they do come in sporadically, and then because of changes in monetary policy, government policies, incentives, and whatnot, right? Or money being driven away elsewhere, right? Because, for example, um, US interest rates reduces, so there's no point putting money there in US, so they move elsewhere, maybe move to Asia, partly coming to Singapore, and so and then suddenly the stock price goes up. So it can happen that the stock price can go up and down, right? And can spike and then fall. Uh, Kind of not so according to real life physics, real life rules, because of the ease of movement of money. But if there's a cap, if there's an artificial cap, say the stock exchange says, of course, this doesn't happen, but if the stock exchange caps it at, oh, your price movement cannot go more than 5% any day, then even if a lot of money comes in, they can only max out the 5% stock price for that day, right? So if you watch day to day changes, it'll be 5%, 5%, 5%, 5%. So it becomes like a very gradual increase that is managed, right? Because the money actually would have made the stock price shoot up 50% in 1 day, but couldn't because of artificial rules that cause it not to do so. So artificial rules tend not to make the current value depend on the previous value, or it could, right? But naturally occurring measures will tend to do that, right? So most of the time, that is like inflation. Now, inflation rate is like for example, consumer price index and all that. They are artificially created, right? Because it's an average over the prices or the price increases. But then look at the price increases. Those prices, the ingredients that participate in that averaging formula, those prices come from what? Come from food, clothings, housings, transportation. These are driven by the actual usage, right? The society kind of acceptable price changes. Those prices cannot double overnight, or hell will break loose, right? So those prices cannot drop to zero overnight, or else chaos will happen too. So it is very much monitored and controlled in that sense that the businesses want to charge more for profit, but they cannot just artificially double the price overnight. They can't, right? They want to attract business and give promotion. They also wouldn't all of a sudden zero out their prices for all their products. I mean, you don't hear that. That means it's collapse of the business, right? people will start snatching up the products. So because of all these mutually enforced forces, opposing forces, so the prices tend to be stabilizing in a dynamic way. You want to go up, sorry, I will complain, right? You want to go down, consumers want the prices to go down, businesses will say, well, no, I'm not going to give up my profits, right? So there'll be kind of a tug of war, and at that right tension, the prices will start to creep slowly up or down. Yeah, given the environment, the business environment, the overall business climate. So inflation rate tends to increase slowly with time, tends to decrease slowly with time, and it will be dependent on the previous inflation rate. We will be surprised if we see that in let's say they always announce inflation rates right from the Fed discussion. So inflation rate 2%, 2.4%, and the next meeting they say inflation rate now has tamed down to 2.1%. We can consider, you know, uh, reducing the high interest rates or whatever it is. So they 2.4% down to 2.1 is also quite drastic already, but then it's still acceptable. 2.4% drops to 0.4%. Think about that, right? It would take a lot of price falls, right? Like all prices fall rather significantly or at the same time, then it will lead to such a drastic fall. But then imagine what would the society become, right? In that time period that led to the observed 0.4% consumer price index, it will be chaotic, right? So it will not be having drastic relatively speaking, right? But no matter what, inflation rate depends on its previous value, especially over the right time interval. So for that matter, we have interest rates, and many of these rates, even though they are financial rates, they are artificially crafted formulas, still very much versus time. Very much that the previous value drives the next value. So we have sales versus time. So for companies, especially mature established companies that sell to public, right? Like consumer goods, fast moving consumer goods, shampoos. So P&G, Unilever, right? They sell shampoos, they sell laundry detergents and all this. Now, can they double the price? There'll be a lot of complaints. There'll be a lot of noise. So much so the government will step in. Why are you doing this, right? So they cannot just unilaterally just do that unless there's a change in the environment, right? So sales for this kind of companies' products, they are already established, right? They have a steady customer base. Their products are used by a lot of consumers, right? And so they're sold all over the world. So it's very like stable. It's like a big tree right now. Yeah. Can you double the prices? Can you double the volume of sales? Will people suddenly overnight wash their hair 3 times a day rather than 1 time a day? Change their practice, change their habits. It's tough, right? It's unimaginable that people change their habit overnight. Can people change their habit over long periods of time or over a decade? Sure. Like Singaporeans are continuously being educated, right? Through campaigns, through advertisements, through slogans, through reminders in our bills, everywhere to watch our use of water. You hear it once, you hear it twice. Just government saying that, right? You don't pay attention. You hear it 3 times, 30 times over a year in various places, right? 300 times over 10 years. And gradually you say, well, perhaps I should play my part. Okay, you're not being forced to, but you're just being educated to gradually appreciate that Singapore is small, every water droplet is very precious, right? We cannot manufacture water at least not cheaply. It takes a lot more water to make one drop of water, so it doesn't make sense. So we better be very prudent and use only that much water. Okay, so finally we get it. Right? So it's like over time, yes, the water usage per person and therefore the whole country decreases. Right? So that would be a sort of a managed campaign to drive the usage of water down. So that is basically right how the dependency can happen right gradually when you measure long enough time. We cannot be overnight halving our use of water. Maybe we did do that, right? So when we were young, we shower and then just let the water run because it's fun, and we don't care about water saving. But when we are adult, maybe we end up using less water than we were a kid, even though we have a bigger body size, right? To bathe, to whatever it is. And how did that happen? Or because we are more conscious. So we can be educated to reduce, right, our water usage. But can people just do that in one day, in 1 month? Yeah, so that's what I'm trying to say, that the dependency is there. The sales, whether you talk about dollars or volume, right, cannot halve, cannot double. For the company, they want to double it, but that's not possible. For the people, they want to save on buying the laundry detergent and shampoo, right, and shower gel and the toothpaste and all that. I want to halve it, right, if I can. But tough, right? I cannot do it overnight. But with practice, with printing reminders or sticking all over my house, my toilets, then maybe I'm reminded again and again, and I would urge myself, discipline myself a little bit every day, and finally, over a period of maybe 3 years, 5 years, I could, right, finally reduce by 30%. Okay, maybe not half yet, but a significant reduction is observed. But that's not overnight. So again, the range of your sampling of time interval, the time interval itself, and the range, they dictate the magnitude, the strength of the autocorrelation. So, but all these inherent dependency on previous sales, it's already there. If I'm a big water user, right, I have the habit of showering 5 times every day, then when I manage to finally reduce my use of water, probably it'll be 2 times every day. Yeah. If I am a person who showers only once every other day, once every 2 days, when I finally reduce my water usage, it may be that, oh, okay, then in that case, it's a good reason for me to shower once a week. And that is the kind of relative reduction that we are talking about right now. So the dependency on the previous value is still there, although the magnitude of the absolute quantity is all different from people to people. Others could be unemployment rate, productivity, and so on and so forth. Right, so basically a lot. If you can already see the pattern here, right? So they are all finally, although some numbers like interest rates, consumer price index, all these, they might be formula of combining other variables into one, like taking the mean, taking the median, whatever it is. Those ingredients that feed into this formula, they themselves, they are generated by ultimately people, right? Or if you're talking about, say, studying, pets' behavior, so it's about dogs and cats and animals, right? So if you're talking about that, then ultimately it's also about those animals' behavior, which is going to be biological, organic, and hence dependent on the previous self. So for a particular species of dog, the maximum size it grows to, whether you're measuring the overall length from head to tail or weight, right? will be dependent on its previous rate. If it's a small kind of dog, small breed, right, then it will still be growing. It will still be growing just like human, but maximum size is this. If it is huge kind of dog, then it will still be growing, but it will be growing at a faster rate while young, and then the overall size and weight will be larger, right? But it will not become infinity. It will not become something out of control, right? Yeah. So again, a lot of these organic, biological, and naturally occurring, for example, the number of trees in the forest. Right? Again, it cannot double all of a sudden. It will grow and grow and grow, right? But it won't suddenly double in density. So all these things, they are pretty much within our expectation of daily life's behavior. So in that case, then the number over time, right? So time is a variable now. Remember, that's what we started talking about this. So if time is a variable inside your exponential variable, then you better be careful that this autocorrelation, my current value depends on my previous value. That might exist. Okay, so if that exists, then that means there's embedded tangent gradient there. Because if I depend on my previous value, that means there's growth rate, right? Because we are dependent on time. If there's growth rate, then that means there's embedded growth rate within the response variable. So the embedded growth rate might be accelerated. That means there's acceleration in the growth rate. That means d square y over dx squared. Instead of dy dx being a constant, it may not be a constant. So if dy dx, the gradient b3 here, is not a constant, then we are in trouble. So that means we are trying to use a linear model to mimic or reproduce a non-linear data set when time is involved. Right? So when time is involved, basically, there can be new problems to take care of. Okay, so today we want to look at what is this very time-related problem called autocorrelation. Okay, let's look at autocorrelation. Auto means with itself, with myself. What do you mean by with myself? With y. We're talking about y, right? So the y has correlation. You recall the correlation, right? So x and y, are they correlated, linearly correlated, right? So is y correlated with y? That's always a 1 if time is not involved. Am I correlated with myself? Using the y sample, you correlate with y sample itself, is a 1. Perfect correlation. Perfect. Positive correlation. If I change, I change. If I change a lot, I change a lot. That kind of meaning. But when time is involved, we're talking about, am I changing a lot of over my previous self? And there's now a sense of previous, because we're talking about t minus 1. So if we talk about phi 1 as autocorrelation of order 1. Order 1 lag. And lag means shift. My GDP this year depends on shift 1, order 1. So my GDP this year depends on last year's GDP, which is oftentimes what we hear, what we read in the news reports, right? A year to year, there is a 1% increase in GDP. That's year to year. Of course, with previous year, not of the next year, right? Which hasn't come. Not of 2 years ago. Definitely not, right? So it's always year to year. When we report numbers like that, and the 1% always is more or less there, 0.8%, 1.2%, yeah, negative 0.1%, that 1%. Okay, so it's always hovering around that percentage. Then we get a sense that it is likely to be a autocorrelating sequence of numbers. Because remember, if I am growing 1% this year, next year, and following year, let's say they are all 1% of the previous year. If I start off with $100 billion GDP, then my 1% growth is 101 billion, but then the subsequent year is 1% of 101. So it's compounding now. It's more than 102 already. And of course, you can say, okay, after rounding it's 102, but then it doesn't go like that. Going 10 years into it, you're going to get more than 110 billion. You're getting much more than 110 billion. So percentage growth is a little bit like compounding effect already, right? So that's why we will strongly, when you hear things like that, you should now suspect that there is a autocorrelation, or there can be. We need to check. Hopefully we don't have, but unlikely. All right. Company has been increasing its sales quarter to quarter about 2% every quarter. Okay, right. So that is another triggering point. So when we regress, if you didn't put in time, perhaps it's okay. But if you put in time, if you're studying whether the growth in number of employees affects company sales, there's no time, right? So fine, then it's okay. But when you plug in time as well, right, number of employees and time try to explain the growth in our company sales. And yet you've been hearing news like quarter to quarter growth, year to year, quarter to quarter growth, right? 2%. Then we better check for autocorrelation. Huh? So here, the idea is that the total autocorrelation correlation is, of course, something to do with covariance. Okay. And the denominator is going to be the sum of squares, because the divide by n or n minus 1, they cancel out. And we are only looking at the y values. Okay, the y values throughout the times 1 to n. Yeah, each y value of the y bar, then square. So it's square of deviation. So this is quite understandable, right? This is like the numerator of the variance of y. That's all. So it's like SSY, essentially. But the numerator is where the magic happens, right? So the I is going to starting from 2. We would like it to be 1, right? We would like it to be 1, but because we're going to shift the y, it means we're going to make a copy of y and shift it a little bit so that we can say at that time t equals to 2, y1 explains y2. At year 2, GDP of year 1 multiplied by 1.01, right, or explains, right, year 2 accounts for GDP of year 2, right? Now, yeah, so we got to shift by a little bit. So the autocorrelation is going to be y of this year away from the mean, no square, because we're going to multiply by y of last year, t minus 1, away from the mean. Okay, and because we're going to have last year, I has to start at 2, the index I. Did we use I or t? T. So the t starts from time 2. So 2 minus 1, right? 2 minus 1 is 1, so then this would make sense, and the 1 deviation is multiplied by the 2 deviation. Then, of course, the 2 deviation is multiplied by the 3 deviation, right? And so on and so forth. So we add up this part. And the 1 here, right, the 1 here is the order 1 lag. And if we were to have other orders, then we would not minus 1, we would minus 2, right? But then if we minus 2 means we're going to shift 2 cells down, we better have a lot more data. The more lag we are trying to study, the more data we would have to skip, right? Because we need more data to form the lag. Then we can see what's the effect. It's like saying that to study the lag 2, order 2 lag, autocorrelation, we need year 1 and year 3 data, skipping year 2, correct or not? See how the 2 years ago the GDP influences this year's GDP. And that can happen. Why? Because government policies, they may say that to encourage trade, I give you rebate. But you cannot claim rebate immediately for this year. You have to claim 50%, 50%. Or maybe you claim 60%, remaining is 40%. Okay. No matter what, the effect only dies off 2 years later. Now it's artificially created, right, because of the government policy. And the government policy is trying to sort of make sure you don't sort of trade and then run away. You have some carrot to continue trading, and the second year you make more trades, and then you have more claims in the third year, so you continue to trade. More like an encouragement because government doesn't have to give you rebate, right? But I give you rebate, but I hope that you won't run away with taking the rebate and then go, right? I would also like you to stay, but I don't want to have a rule that say you cannot go away, right? I mean, if you want, you go, right? But you just give up your rebate, which is not available to you after all, right? The government didn't have to give you the rebate. So, assuming that kind of policy is crafted this way, then we should expect that because Singapore has a lot of trading companies, it's a trading country, right? So, the trading companies will trade and then claim rebates. For example, this rebate I don't know if it exists, but assuming if it exists, then the companies will claim, right? And Singapore is stable. Most companies will be very happy to continue staying, and then they can claim some more of the leftover 40%, right? While doing more trades. So why not? So they will claim the rebates, the 40%, only in the second year after the trade was done, right? And so the lingering effect will be created because of this policy, which is artificial. Artificial because people created this rule, government created this rule, not a natural phenomenon in that sense, right? Because this can also be taken away. Like after implementation, this doesn't seem to help the GDP at all. Okay, take away. Don't lose money, right? Something like that. Okay. So if this policy were implemented, then we'll see a GDP 2 years ago can influence this year's GDP because of the rebate, right? And the autocorrelation will have to take into account the lag 2 effect, the order 2 autocorrelation. So then we will do a phi of 2 calculation. That basically is the idea. Okay. Now, this is just a definition, and it can look a little bit intimidating because we got to think of the lag, right? So let's start with a bunch of collected GDP data, but we're not going to use the actual GDP, just something very simplistic. Okay, let's say we have a 6, 5, 7, 6, 8, 9, 7. Essentially, these would be because of the time being 1, 2, 3. You can think of these as quarters or years. So we have 7 time units. Typically, when we come down to this numerical scenario, we don't have to worry about the details because whether it's measured by quarter, day, month, year, doesn't matter anymore. We just concern ourselves with the numerical number crunch. So what I'm going to do is to calculate the autocorrelation of this bunch of y values. By first, we need the y of t minus 1 and the y bar. Y bar is everywhere, right? So first we calculate y bar. My bar is 6.8571, and our y t of minus 1 is going to be a copy pasted and shifted value. Always remember that we want to say use the GDP of year 1 to measure or calculate for the GDP of year 2, right? So we want to align the 6 with 5 and the 5 with 7. And after a while, you just basically will see another way to do this, which is copy, then shift down, right? This way of thinking is easier. Let me just finish writing first. 8, 9, and you see that the 7 is being skipped off, right? So mathematically, what we want is that, this is the shift, right? So this is the shift, but programmatically, when you use R or Python, or for that matter, even Excel, you can do it. You should do the whole vector copying, copy paste, then shift down by one cell. That's a lot easier to do programmatically. No? So, but the thinking is to do this. We want to use 6 to autocorrelate with 5, or to try to explain 5. See if there is strong or weak, positive or negative autocorrelation. Notice that there is a numerator, there is no squaring. So it can be minus times minus, like covariance. It can be minus times plus, resulting in a negative autocorrelation. Also possible. Also possible. Positive autocorrelation, right? The last year is 1. Next year is 1% more. Next year is also 1% more. So it's positively growing. Okay, so this could be GDP, this could be population of a young city, this could be whatever it is, some kind of compounding even. Negative autocorrelation, GDP this year is 100 billion, next year is 99 billion, subsequent year is another 1% lesser, another 1% lesser. Okay, so it's like a falling GDP, right? By percentage, not by 1 billion every year, but by 1% every year. So it's going to be more than 1 billion several years down, right? But the first is just exactly 1 billion. That's the difference between just subtracting 1 billion as a constant and multiplying by 0.99. Okay, so then what? Then we want to calculate two things. We need this and this, right? So we need y or at time t minus y bar, okay? And we need y at time t minus 1 minus y bar. So because yt minus 1 doesn't exist, undefined, right? Because we are talking about time 0, which is undefined. So we're going to skip this. This doesn't exist. And we will just be doing yt5 minus 6.8571. So we will get a negative, this will get a negative 1.8571. 8571. And because we are minusing y bar, we can just simply do it as well. Because the denominator includes time 1, which is defined. This one is defined, so we should also do that. And we get negative 0.8571. Now, I won't want to keep on writing all the 4-digit numbers. This is not a lottery comparison here. Because the rest will all just be 7 minus 6.8571, right? Okay, then 6 minus, so we can just do that. But I just want you to be clear of what I'm doing here, right? And also to check that, the first 2, you get the same digits as me. The rest, you will see some sort of a 1428, 8571 and all that stuff. And I just give you the last 2 so that you can compare and make sure you are on the right track as my calculation. 29, and the last one 0.1429. All right. Yeah, so because the formulas are the same, so you can just repeat and paste. I don't need to show you the rest. Because if you're right on these 4 numbers, you should be right for all the numbers there. And for yt minus 1 minus y bar is you use this column. And the first, now I'm talking about this first cell, which is blank. So this first cell is blank. Second cell is to use 6 minus 6.8571, resulting in negative 0.8571, right? Negative 1.8571. Again, all the way down, right, to 1.1429 and 2.14. Okay. All right. So now the sum product of these two columns. Okay. Which two columns? These two columns. We want to perform a sum product. A sum product is simply that with the first cell times the first cell gives the first cell times the first cell plus the second cell times the second cell plus the last second last times the second last plus the last times the last cell, right? Which is the sum product of y t minus y bar, y t minus 1 minus y bar. So that gives us 2.9796. Did you get that? Okay. Even if you use calculator, you probably can do it. But you can do this in Excel, in R, in Python, very easily using NumPy. Okay. Then next we have sum of the squares of this one, everything. Okay, because the definition is over the entire t equals to 1. Now, some software, namely in Python's stats models .tsa time series analysis, there's a parameter for you to say, okay, I don't want everything. I don't want to match the skipped sample. So if my summation is over from 2 to n, I want this to be also from 2 to n. The adjustment, that means we will ignore this one. You have a means to tell the function to ignore this one. In other words, you can try to standardize the number of samples involved in the autocorrelation, although it is also acceptable, right? Officially to include everything in, because it's easier to calculate everything, and we can do that, right? So for small lag, that means low orders, order 1, order 2, order 3. That means you skip 1, 2, or 2 or 3 relative to the sample size. If your sample size is large, then order 1, 2, 3 small orders. Include, don't include, you're not changing the denominator by too much. So then typically the autocorrelation, if it's positive, if it's negative, the conclusion remains. Whether you choose to skip or not skip the first few so-called error squares. All right. But when sample size is smaller and the order is large, like order, we are not calculating order 1, but if we calculate order 4, then we are like almost like dropping off more than half the data, right? Then it can be very serious in terms of the conclusion. When there is no autocorrelation, you can conclude there is, right? Simply because you're picking only the last 2 or the last 3. Then we need to be very careful. So small sample size is always not a good environment context to begin with. As we all know, in all statistical calculations, touching reality only small number of times, not good. But here we're just illustrating the formula. So here, this formula, we're trying to, of course, do the sum of squares, yt minus y bar, itself 2 times. It's like I copy yt minus y bar times itself. So that's why it's auto. I square it because it's 2 copies of that. So my number is 10.8571. Okay, and finally I get the autocorrelation. Phi of order 1 is 2.9796 over 10.8571, and the ratio would give us 0.2744. Okay, so there is some slight positive autocorrelation going on, and whether it's serious or not depends on our own assessment. So even though everything is based on data, formula is always well defined, you and I will calculate the same data, we'll always get back the same autocorrelation. But is it serious or not? Is this positive autocorrelation bad enough, right? Is up to our assessment. Depends on what these numbers mean. All right. If it is progressive test scores, my own test scores, right, and I'm seeing autocorrelation positive, good. Something like as time passes, my scores are improving upon the previous scores. Maybe this is GMAT score, TOEFL score, then a high positive autocorrelation could mean I have a high learning rate, a term that I borrow from artificial intelligence for my actual intelligence now, right? That I'm picking up, I'm improving really significantly. Every time I do another test, this practice makes me even better, even better, even better. So that's good. But for human, perhaps this is already very good that I'm improving. There is a positive autocorrelation, right? And if it is negative to neutral, that means I'm getting more and more frustrated. Why am I repeating, right? Why do I have to practice? Practice doesn't help. So the more I do, the more frustrated I become because I don't believe in it. And so I have a negative autocorrelation. So I think you can put it in your own context. You can have a feel of that, right? Have a almost an emotional feel of what autocorrelation means. Because we are trying to auto correlate our performance with ourselves, our previous self, right, in the previous time measurement. Okay, so that is the calculation involved. Okay, next, let's look at a test that would allow us to gain a understanding of whether the model, which model, this model, an example model, whether our model has issues involving the residues having autocorrelation with its previous error. Because now we have a sense of what is previous. When time variable is added in, it is meaningful to then say the error incurred at time one, right? What's the error? The error is the model, right? The model producing a predicted y at time one, when we also have a measured y at time one. So then there's a discrepancy. We learned about the residual in the previous sessions, in session 7, sessions 8. And the first error, the first residual, predicted minus the y, does it predict, right? Or is it correlated with, right? Is it correlated with? Is the next residual correlated with the previous residual, right? Or is the time equals to one residual predictive of the time 2 residual, which is itself predictive of time 3 residual, and so on. If the whole residue series is autocorrelated, whether positively or negatively, that means the residuals themselves are predictable based on past values, correct? Because that's autocorrelation, right? That's trying to say that present value depends on the past. Suppose we're just talking about order 1 autocorrelation. And order 1 occurs a lot more naturally, frequently than order 2, 3. Order 2, fine, maybe, right? Like I said, the government policy. Order 3 could also be because the rebate is permitted over 3 years. Order 6, 7, 8, 9, 10, harder and harder to come by, right? Nothing is impossible, but it's just rarer for us to say that, oh, you know what, that phenomenon must be order 12 autocorrelated data series or what. It's just harder to imagine. So while we don't have a maximum for order, naturally occurring data most of the time will be order 1 is sufficient to tame the problem due to the inclusion of time variable. most of the time. All right. If you want, go on to order 1 and order 2, and maybe even order 3, right? But then don't try to think of, I need a very perfect model, so I will try to do 1 to 20. Right? That may not be necessary nor even good for your modeling. Okay, coming back to the detection of errors. Okay, so remember this is strictly about errors. Durbin-Watson test. Right, so let me highlight that this is for errors, the residuals. And we have a good and well-defined formula or definition for residuals, right? The predicted minus the observed values of y, nothing to do with x here, right? So autocorrelation is a concept that can apply to anything. And in my illustration just now, I calculated for the value of y, which is this. You can, of course, calculate for values of weight and income, but our concern in the context of linear regression, right, when we apply autocorrelation, will be of the response variable. Because if response variable itself is strongly explained by, right, is highly connected to its previous value, then there may be a case for autocorrelation, right? So we calculate autocorrelation most of the time for two things. One is the y variable, the other one is the residual. Residual, again, I say the third time now, is different from the y value because the residual is y hat. Maybe it's good to put that in here. Is y hat of t minus yt, not y bar. So it's a vertical difference between the star and the dot. Now the dot is on the predicted line, the star is the data point, like this. In other words, since the y hat is involved, y hat is this entire formula, right? This entire model. Not even here. This one is the data, right? So the y hat is the right hand side evaluated given the same data points as weight, income, and time. So the autocorrelation of errors, in other words, the Durbin-Watson test, is done when you have done the model. Whereas autocorrelation of y, I don't even need to run the model. You give me the y, I can start calculating. So that's the main difference. Don't mix them up, right? Okay, so Durbin-Watson test. Let's look at the test statistic. How do we calculate the Durbin-Watson test statistic? It's always like rock climbing kind of a cliff, and I want to see if I can save this side of the space. Okay, all right. So what is the test statistic? The Durbin-Watson, Durbin-Watson, Durbin-Watson test has the hypothesis of H0 that the population autocorrelation of order 1, right, is 0. And of course, row 1 is not 0. So no auto correlation order 1. Has autocorrelation, order 1. Now, we need to, of course, quantify that. Oops, I'm covering my own writing. We need to quantify that it is of order 1, clearly. Yeah. And we will only talk about order 1. Like I said, order 1 occurs much more frequently and almost like readily. And we need to worry more about order 1 effects because we hear that, we read about that. Just think of the GDP numbers. And next thing, of course, when we put down order 1 is that if there's no autocorrelation of order 1, can there be autocorrelation of order 2? Possible, right? There are some phenomenon it's not so frequent, so I cannot be listing them readily, but there may be a sort of skip 1 year then happen, that kind of dependency. So if that is the case, then perhaps due to policy or otherwise, you skip 1 year and then it affects the performance. So if that's the case, then you have like 0 or very little order 1 autocorrelation, but existing, right, some level or even strong order 2 autocorrelation. In practice, however, seldom, right? I would say very again, I don't want to use the word rare because if it does happen, then it will happen in that niche area very frequently, right? But not easily or commonly experienced by most people. That's what I'm saying. Furthermore, if order 2 happens, then order 1 also tends to be in influence. That means order 1 will influence usually stronger, more, and then order 2 will come into influence, but usually the strength is lesser. It's a little bit like echo effect. When you make a sound in the mountain ranges, the first echo comes back strongly and first, right? Because it gets bounced off the nearest cliff and then comes back. Then after that, your voice will also go on to hit other cliffs further away. So it will take longer time. And because of dissipation, it comes back weaker. So it will come back weaker and later, just like echoes. And typically that is also the case in most variables we measure in real life. Okay, so for now, let's focus on order 1 analysis. If we can arrest this beast, then we should be on to a good start, right? So we now want to see if the test statistic from Durbin-Watson is going to reject the null hypothesis or not. If so, right, just like the global model F-test, if we reject, then model is significant. If we reject here, then there is autocorrelation, which is bad news. Okay, so what do we do with the test statistic? So the test statistic is, with respect to the names Durbin and Watson, DW, right? Similar to the autocorrelation. It's a bit like quote and unquote sample calculation, right? So we do this, right? 2 to n e to the t or e sub t minus e t minus 1 squared. Now, let's look at this one first. This is residue or error at time t. At time t minus the previous error. Now, there is a very, very important presence of structure here. It's like the previous. In performing regression, previous makes no sense, right? Because previous value for weight is not necessarily the same as previous value for height individually. But previous residual and the current residual, they make sense here because we're talking about time. So there is strong exploitation of the sequencing of time, and just as it should be, That means we are respecting that this variable time has sequence, has order. How do we mathematically respect that? That means include that orderliness into our calculation, thereby having different results if the order were to be changed. And that is exactly this t and t minus 1. So the order is not so much the priority of summing the error differences, but rather the lag, the lag in the sense of lag by 1 time unit or lag by 2 time units. Then it will be t minus 2. Okay, so then again, this is a bit like autocorrelation. We will do this as a ratio over the entire residual squared as the so-called total variance without dividing by n or n minus 1, taking the average, that is. Without taking the average, we just do a sum of squares of the errors, right? So sum of squares of the errors, this trick we have been using a lot of times, whether in testing for equal variance assumption in the F-test, we also do that. We just use the sum of squares, right? Then we do that in ANOVA. We do that in, of course, the global model F-test. So we do sum of squares. We're very used to sum of squares, right? But the numerator here is where the structure is being exploited. Now the previousness, or the sense of previousness, is being exploited. And once we calculate this test statistic, then we will be able to obtain a number, right? So this number, right? This number is between 0 to 4. And I purposely stretch it out. Okay, 0 to 4. And it depends on various things, amongst them your significance level, sample size, right? Just like t distribution. But in addition, it also depends on your number of predictors, and that is here, right? So it's like x1, x2, x3. So then k equals to 3, and there are 3 predictors, right? Then we got to look up the right critical value for Durbin-Watson to test to obtain the boundaries. We will use the critical value method to compare with the test statistic here, right? So because for Durbin-Watson, if you look at the critical value table, they will have 2 values, and that's not because it is two-tail. Two-tail, you get 4 critical values, right? Something like that. More because, first of all, for Durbin-Watson test statistic, closer to 0 implies strong positive correlation or autocorrelation, right? And nearer to 4, and you cannot get a value larger than 4. So nearer to 4, you get strong negative autocorrelation. In the middle is the value 2, and 2 has a rather special role in that it means no autocorrelation. Of course, order 1. All right. And then you have, of course, various shades, right, going outwards. So green light here, right? So then you have somewhat of a orange, orange intensity. It's from 2 to 3. There's no fixed number because you're trying to obtain the correct critical values. And when you go on to here, right, it will be negative autocorrelation. And when you go on to here, you will have positive autocorrelation. Okay. Yeah, so just look up the table for Durbin-Watson. You get two numbers for one tail test, four numbers for two tail tests. The two numbers are such that if your test statistic fall between the low and the high number, then it's inconclusive, cannot tell. So you probably have to redo with more sample size or wait for more time periods to gather more samples, and then you can try again. Okay, and so if you're doing two tail tests, you will get four critical values. So if the Durbin-Watson test statistic, falls below or falls above the high of the four, the highest number of the four numbers, or falls below the lowest number of the low number, then you will want to conclude that there is autocorrelation. Okay, when you're testing for yes or no autocorrelation, we don't care whether it's strong positive or strong negative autocorrelation. Because if there is autocorrelation, our regression model is in danger of its reliability, right? We are not very sure we can use it anymore. Remember, the Durbin-Watson test is about the model. Okay, let's write that down. Okay, this test is for the model to test. So it's used for checking autocorrelation of model errors. So if you don't have a model, then you don't need to run the Durbin-Watson test. Yeah, because this E of t you can only get when you get a model, right? You calculate the residue. Okay, so think of Durbin-Watson test as a sort of just like COVID-19 test kit, a test kit to let us know if we are suffering from such a problem in the residue. Okay, in the residue. Now, why would the residue imply anything about the problem about the model? If we have a model, okay, remember this model here, it can also be polynomial, it can also be logarithmic random variables. Remember in our session 8, we talked about that. So it can include nonlinear variables. What would have been our nonlinear variables get transformed, right, in our session 8 into linear variables. So what that means is if our variables, they are able to account for a lot of the fluctuations in y, then what remains should be noise, right? Should be independent even when time is involved, and we kind of like don't give any special care to time. Then what remains ought to be just noise. But Durbin-Watson says, but I'm a sensor that cares about time because you did put in time. Of course, we don't run Durbin-Watson if we don't have time, the time variable in our explanatory variable sets. So when it's involved, then Durbin-Watson says, but I'm going to treat your time here, right? And then check if the subsequent residuals, they are predictable. They are like 2% of the previous value. Remember the GDP example, right? So if errors subsequently, they are 2% of the previous error, right? Later errors, they are later residues, they are 2% of the previous residue, which is 2% of the previous residue, and so on. And therefore, Durbin-Watson is going to be, either near 0 or near 4. right? That means there is autocorrelation in the errors. What does that mean? That means the errors will be larger and larger, right? Remember the compounding growth kind of situation, right? Now, think about it. As time passes, the errors are larger and larger. That is the conclusion. So as time passes, errors become larger and larger in a disproportionate sense because compounding is non-linear, correct? Or it's like an exponential growth. So as time passes, another way to put it is as time passes, residual grows exponentially. Which means what? Which means your model is totally poor in explaining health when time becomes larger and larger because you're making more and more errors. See that? Even that's despite your variable here could have been income squared or weight to the power of 3, or square root of income or something like that. Non-linear, right? Despite that, as time increases, your predicted health and the current observed data, it's growing exponentially. Also, that is revealing the fact that your model is not so healthy. It's unable to cope well when time increases. That's why you see, even if health itself is non-linear, right? We could put in other transformed variable to account for the non-linearity and thereby reducing the residue, the error, the differences between predicted and the observed data, including when time is involved. If our non-linear variables are good, right, they are able to recreate the non-linear shape observed in health, in the Y. But if not, if we didn't transform the variables, let's say, right, and health is non-linear with weight, income, time, then the residual will have to take in the rest of the unaccounted for errors right now because data and the prediction. If your prediction is up to data, error is squeezed out to be 0. If your data and the prediction is very, very huge distance away from the data, maybe at first when time is small, it is very close, so error is small. But when time is large, it has grown exponentially. The gap has grown exponentially. The gap is precisely the residual, the error term here. That is why Durbin-Watson test will go for the error term as the unaccounted for gap, right? Does it grow? Does it depend on its previous self? And that is itself enough to describe a lot of non-linear behavior, whether it's exponential, parabolic or whatever it is, right? If you depend on your previous self, doesn't matter to what degree, very strongly like exponentially, very weakly like square root kind of dependency or whatnot. There is there's dependence on the previous self. There's some sort of a recursive description. Future values are some modified, slightly modified version of the previous value. Then it will show up as rejecting the null hypothesis, right? So then we will doesn't mean that it is invalidating the model. Perhaps we can still use the model because the samples are so rare. We just use for the lower time periods. We don't make the time a large quantity, right, for positive correlation, autocorrelation. And otherwise, we may try to slice the time and whatnot, do other things. So we can do some reactive measures depending on what the outcome is, right? So that's why Durbin-Watson has a very general ability to help us detect time-oriented errors, which is autocorrelation. So hopefully now you understand why we look at the residuals. Residuals is like CSI detective digging out the rubbish, the unwanted residual, right, from the so-called criminal, right, the potential accused. You must have left certain rubbish, right? So I look at the rubbish, I can take out a lot of extract a lot of evidence, right? whether the food you ate, the shop you bought the food from, the DNA, the saliva, the whatever it is, right? So we can extract from it. And that is what Durbin-Watson is doing. Totally to number crunch and microanalyze the residuals and exploiting the structure to detect dependency about this previousness. So other tests don't quite care about t and t minus 1 and also cannot care about I and I minus 1 because in other regression models that don't involve time, the ith sample and the I minus 1 sample, they are supposed to be independent first of all, right? So doesn't matter. Okay, let's take a look at an example perhaps to help bring out the so-called power, the effectiveness of Durbin-Watson test, right, in helping us to detect autocorrelation, and then we see how we should react to it. Okay, so perhaps we can use back our example here. Over here, all right. So our example starts with this y equals to yt, right? Yt 6, 5, 7, 6, 8, 9, 7. And we were saying that this is because we are using time equals to 1, 2, 3, 4, 5, 6. Okay, now suppose we just do the usual linear regression, in this case, simple linear regression, right? So our model is going to be, our intention is going to be yt is equal to b0 plus b1 times t, right? So using t to explain yt. So if yt is GDP, then we say as time passes, time explains GDP, right? So as time passes, Singapore GDP grows. So time is an explanatory variable. Although it sounds strange, that's what is coming out from linear regression, right? So time is an explanatory variable of GDP in our response variable here. If we do that, then what happens? If you just do your number crunching, you will get we get B0 is 5.1429 and B1 is 0.4286. Right. So the model is completely solved. We get this. Okay. How do we know if it is suffering from the time illness, and that is autocorrelation? So what we do is we will calculate for y of e, our predicted y. Okay, so our predicted y is y hat of t. Predicted y is going to be 5.5714 by just plugging in 1 into the model here. Right, so we have our B0, B1. So you can calculate yourself. I just give you two numbers. Second number is 6.0. And then I will spare you the rest all the way to the last number, 8.14. Okay, maybe the last one, 8.1429. rounding to 4 decimal places. But if you have more decimal places, please keep them. So we have these, all right? Then we have the errors. So the errors will be E of t. E of t. Right? E of t is going to be y hat at time t minus y of t, which is this minus this. Right? So these two give E of t. So like these two give E of t. Okay, so y hat minus yt is the so-called correct number. We don't doubt the data. Right, so my E of t is negative 0.4286. Second value, easy, 1.0. Third value, you keep going, all right, all the way to the last one, 1.1429. Yes, did you get the same? Okay, so that's the signed error difference. And we need the signed error difference first because the second term here is E of t minus E of t minus 1. Oh, okay, just watch carefully, right? So we are talking about this term E of t minus the E of t minus 1, the 1. Okay, so the first term, we are going to talk about t0, which is non-existent, right? So this doesn't exist. Cross out. Second term is 1 minus negative 0.4286. So we get 1.4286. Third term, right? So is I get negative 1.5714 because it is negative 0.5714 minus 1 here, right? So you get this, and so on. So again, I will spare you all the numbers here. 2.4286. If you get your ET correct, and the first two terms of your ET minus 1, then it should be safe for you to get the rest of the numbers correct. All right. Let's do a quick check. So sum of squares. Sum of squares, we get sum of squares. Okay, so you can do sum of squares very easily in Excel, sum SQ, right? R, even easier. Python, straightforward, right? So you can do that. The number I get, 5.7143. Then the sum of squares of this. So let's do that. This one. Okay, goes to this guy over here. And we have sum of squares of ET minus 1. Right. If you tabulate this column, then it's very easy. Just do the repeat sum of squares. So 15.2449. Okay, so this time round, this, right, sum of squares, square each term and then add. And this gets recorded here. And Durbin-Watson is none other than just dividing 15.2449 by. So Durbin-Watson, right, is 15.2449 2449 over 5.7143. So we get 2.6679. Depending on what is the alpha sample size, we have 6 here because we threw away one. Huh? We have oh no, we included that. So we have 7 here. So depending on your choice of alpha, right? Because our k is 1, we have t as the only time variable, one explanatory variable. So depending on your choice of alpha, we will end up getting 4 values, right? So DLD, DLD high, and then another DLD on the left side and the right side. So this is leaning towards the right side, meaning there's a bit of indication of negative autocorrelation, which is, of course, not in agreement with our slightly positive autocorrelation. So perhaps in the end, it's inconclusive, or it is not strong enough. The autocorrelation, whether negative or positive, is not strong enough to make Durbin-Watson reject, so that we would say there is no autocorrelation, right? So perhaps it doesn't matter. That means indeed, right? Indeed, well, this is not GDP data, so it shouldn't be indeed. But suppose this is GDP data, then if we fail to reject, then it is okay, an acceptable model, at least for this set of GDP data for Singapore for this time period. Okay, but as time passes, Singapore may change its economy, the structure and activity and all that. Then GDP may be more susceptible to fluctuations. Then it may not be dependent so much on its previous set. Right? So there's some dependency, but not so strongly. So in this case, it seems to be not so strongly positive, not so strongly negative. So there's some fluctuation. So maybe after all, it doesn't matter. But that's not what I want to show you, at least not completely. What I want to show you is, what if we use an auto-regressive model? So we use an auto-regressive model. What is an auto-regressive model? So let's say we use auto-regressive model. Of order 1. This means once you see the pattern, you will be able to understand this rather deep word, right? Auto-regressive model. What is that, right? But actually, it's very sleek, and idea is very simple. That is, I'm going to explain why with y itself. After all, right? After all, Durbin-Watson test says reject. Let's say this is a number that is so positive that it rejects, right? So we reject and say there is autocorrelation, and we noted that it's slanting on the positive side, positive test statistic, more than 2, that is. And so there is some sort of, we don't know whether it's strong positive, strong negative, and how strong. We're going to say YT is going to be explained by itself, right? So some y-intercept and its previous self, correct or not? Yeah, it's some sort of a 1% of its previous value, correct? Except we don't know it's 1%. Maybe it's 1.133%. Maybe it's 0.994%. We don't know. So we're going to let the data tell us. But the whole thinking, don't you think, is exactly trying to find y-intercept and the gradient. So we just use linear regression of YT using explanatory variable, shifted y values, and that's it. And because these are numbers in real time, these are numbers happening historically from y of t, it is possible for us to do it. That means we're not twisting time. We're not trying to use future values, future GDP to back project to present. We're not doing that, right? So this is completely feasible. We are not flipping time upside down. We are not doing something that is against physics. So we can and we will do that. And so in what happens next is that we are going to do exactly this. So first thing first is we will use y of t minus 1 to regress with y of t. Or just to put in place explanatory response, like this. So y of t is very simple. We just copy 7, 6, 8, 9, 7. Yeah. And y of t minus 1 is, you see, we would like to use the previous value to explain the next value. So we like to say GDP of year 1 explains GDP of year 2, not the other way around. Huh? So don't shift wrongly. Don't shift upwards. End up you're going to use, 7 to explain 5. Then you're talking about using year 4 to explain year 3 GDP. Then we have a problem, right? So shift it down in the sense that we want to say use 6. You see, by now we lose time already. We don't have the t involved. In our model here, we don't have a time. And if we don't have a time, then we are not implanting another potential source of time-related problem, you see. So no doubt, yt and yt minus 1, they themselves, the values themselves are affected by time. But time is not in our arena, not in our model. So we are not introducing the time-related issues for linear regression. So anyway, using previous value to explain 5, 6 explains 5, 5 explains 7, right? So after a while, you get to see that it's again shifted like the way we calculated our autocorrelation. Okay, so importantly, it is this way, right? You don't shift the other way around, then we will be in trouble. We are like saying using next year's GDP to explain this year's GDP, right? Then you don't need a model. That's just talking about history, right? Okay, anyway, what do we do? Very simple. We just pipe into any linear regressing device, which by now you should be very, very familiar. And we would get B0 equals to 5.1077. That's what I get. And B1, the gradient, which is the growth percentage, remember? 0.2769. Okay. In this case, it'll be bad news as GDP, right? It's like saying that next year's GDP is 27.69% of previous year's GDP. That's collapsing country. Huh? So we hope we are not in that situation. But end up, I think, if you plug in GDP, yeah, your B1, the gradient, will be then interpreted as growth rate, right? Like compound growth rate. In like 1.01 would mean 1% growth every year. So yeah, so that would be how we can expect the numbers. For now, it's just regressing using some randomly generated integers. But we see that we can then calculate all these again, right? So we will calculate E of t, same thing, just to be fair comparison, and E of t minus 1. Yeah. So E of t, we will be creating, need to shift the values because in order to get E of t, I need to get the predicted value. And I think it's a good idea to show you a few of those predicted values. So first predicted value is y hat of t, right? So which means we plug in the 6 multiplied by b1 and then add the offset. So that whatever x value we use to derive our b0, b1, we would now use back the same x value. Has to be, so as to get the predicted value for the same x, for the same explanatory variable value. So if you do that, then the first number you get should be 6.7692. Just to give you another number, 6.4923. All right, and then you keep going all the way down to the last number. I get 7.6. Exact. Okay, now we can calculate the E of t, because it is y hat of t minus yt. So this we can calculate. We get 1.7692. Okay, another number to go with, minus 0.5077. All right, and then okay, let's jump all the way down to the last number, which is exactly 0.6. And we also need E of t minus E of t minus 1. Right, so that's why we cannot square it right here, because we need E of t minus E of t minus 1, not E of t squared minus E of t minus 1 squared. So we rather keep the signed E of t. So which is to say, in order to use an order 1, right, AR1, AR1, auto regressive order 1 model, we lose 1 time unit, right? Because we need the sort of like, we wait for 1 year of GDP so that we can start saying, okay, next year's GDP is going to be 1% additional to this year's, right? So for this year, if we are starting this year, starting our records this year, we cannot predict for this year. So we have to skip 1 year. So our prediction also will skip 1 year because we don't have an X to go with. So we will skip that. And because of that, our error will also skip 1 year. And now for error to happen, we have to skip another error, which means now we'll skip 2 years, because only after, only at the end of the 3rd year, we will have this second error term here, which is negative 0.5077 to minus off 1.7692. So when we do this subtraction, we get negative 2.2769. And now we lose 2 terms in this column, right? So we lose 2 terms. Let's just note that. All right, so that is the structural gap introduced by our formulas, which exploits the orderliness of the time series data. So this is time series data still, because there is time involved, but this time involvement doesn't plague us because there is no time variable directly participating in the explanatory variable, right? So it's okay. Nevertheless, is to justify for the meaning of ET minus ET minus 1. Does it make sense to say the previous value? Answer is yes, it still makes sense, right? But just to give you another confirmation, I will list the next error, 5538. And all the way down to the last value, which is 2.2769. All right. Okay, so just like before, we will obtain the sum of ET square, right? Again, we'll square each number and then add them all up. Right? So for this, I get 9.1692, 9.1692, and the summation of ET minus E of t minus 1 squared, I get 18.166. 666. So our Durbin-Watson value will be the sum of ET minus ET minus 1 squared. So it's 18.1666 over sum of ET squared. So it's 9.1692. Okay. All right. So now what happens? I get 1.9813. Okay. Now, very, very honestly, I didn't massage or tweak numbers such that ultimately I get such a nice Durbin-Watson number, like almost exactly on 2, which is to indicate that no matter what your alpha, you're not going to be able to reject, right? So there's no autocorrelation. There's no autocorrelation. This one, depending on the alpha you choose and the critical values, right? If the critical value is maybe 2.2, 2.3, 2.4, it's just above, right? So then you will end up rejecting. So, or may not reject. So this part not so clear, but there's a slant towards the 4 side, which means not totally non-autocorrelated. That means some autocorrelation. But here, it is unlikely to cause any rejection. Thereby, we conclude that there is no autocorrelation. Right. So in this case, this implies likely to be some autocorrelation. Right. And this means no autocorrelation. Order 1, of course, right? And this is great because we are now able to then very, very sleep well, because we know we're not going to be plagued by potential accusation that, hey, you know what, GDP data, you're not supposed to use time variable, right, in your linear regression models, so that autocorrelation may come in. Did you check for it? Yes, I did check. Number one, I didn't use time variable, even though my data has some sort of a time-based sequence, the YT and the YT minus 1. And number two, if order 2 if order 1 autocorrelation exists despite using this, right? Despite using the order 1, I still have order 1 autocorrelation, then it would show up, and end up it didn't show up, right? So I am totally sleeping like a baby. I'm not worried at all, right? So this is a very good model, right, to account for the nonlinear growth in GDP as time passes, right? So the GDP grows, and it grows at constant rate, like 1%, or more or less constant rate plus noise. But that would have been totally accounted for by the C1 value here. And of course, now that I said this, I should change this B0 to C0 and B1 to C1 so that it makes sense. Okay, so that's our AR model, AR model, auto-regressive model of order 1, AR1. Okay, so advantage is whenever your Durbin-Watson shows that your original model, where's our original model? Right, this model. Our original model has or is suffering from some sort of auto-regressive behavior. And in practical purposes, auto-regressive behavior typically means order 1 auto-regressive behavior. Then the Durbin-Watson test statistic will be our lighthouse, blinking, 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 right? Telling us potential problem. And when we try this, but perhaps because of that, right? because of this indication by Durbin-Watson test, we use an auto-regressive model. That sounds super professional, right? But the whole idea is very simple. Right hand side, use back the response variable, but the previous timestamp has to be previous, right? And you can also say plus C2 y of t minus 2 if you say that there is order 2 influence, right? But you're going to test for that. And when you do this, this becomes auto-regressive model. Okay, so it sounds tough, but it's very simple idea. And when this happens, we have the benefit of testing it again, and we see that it no longer is suffering from autocorrelation in the residual, which is stronger, right? Which is the conclusion from this residual analysis is more generally applicable to the model, right? To say that the model is not having unaccounted for excessive growth in the residuals. So that means the model is more useful to us, more reliable, the integrity is higher. Then for us to analyze the y of t, which is to just calculate the autocorrelation. The autocorrelation is just the y of t, just the standalone y data values, right? And that is enough for us to calculate. So we can arrive at a conclusion of positive or negative autocorrelation, but that's just like saying that we obtain a sample, we take the sample mean. If the sample mean is large, means the population mean is large. If the sample mean is small, we say the population mean is small. Like we're not doing hypothesis test, not a very all-rounded test, right, to make conclusions about the population. And number two, we haven't even attempted to account for or to regress a model for y of t, right? So we have no regression model. But over here, Durbin-Watson test requires us to first make a model. Okay, you can make a simple model, difficult model, right? Then Durbin-Watson will number crunch the residuals, like dig out from the dustbin all the trash and see if the trash still has remaining food, right? The food is still solid, right? And they are not expired, and you throw them away, right? So that is going to cause a problem, and Durbin-Watson will then reject the null hypothesis and make us think again, right? So we think again when you reject the null hypothesis under the Durbin-Watson test, you can then consider a autoregressive model, typically of order 1, and that means use the response variable's previous self to explain the response variable's current self, current value in this sense. Okay, so with that, I hope you have expanded your statistical skills to be able to deal with more complicated data, especially when time is part of the analysis, and time is almost always part of everything's analysis because time is money, right? And business is always involving money. And time also affects our life, affects nature, affects everything that we measure. So armed with this skill, then hopefully you can deal with these data a lot better. Thank you very much for your attention in this video. See you in the next one.